just unmute and ask. So yeah, let's get started with the first unit. So just a quick overview. Here are the concepts we went over in the first unit, right? The idea of voltage, the idea of current and resistance. We'll go over these more in depth later. And then we also talked about two other devices, the capacitor and inductor. So we have the capacitor, which stores electrical energy, and the inductor that stores magnetic energy. And then we have three other main concepts, which is the idea of power, the idea of flux, and the idea of impedance, which we'll talk about later on. And then here are the units, because with science, we always work with units. So with voltages, we have volts. This guy called voltage named it. Current, we have amps, resistance, ohms, and then here are the other ones. They're just good to have. If you want to reference them, they're always in the beginning of the slide, so you can take a look. Yeah, but these three are mainly the ones I'm going to use. These three, and then power. Outside of it, I'm not really going to use units, because we're only going to do calculations with these four things. All right, so let's get started with the first thing, which is the idea of capacitors and conductors. So does anyone remember what electrical potential is? Like, what was electrical potential? Yeah. Anyone remember what potential difference is, or like what potential is? Stored up energy? Yeah. Okay, so I see the idea of voltage in chat, and I see stored up energy. Yeah, so potential difference is something called voltage, but we can think of potential itself as energy. So potential itself, it's kind of like energy, right? Like a ball falls from high to low, right? When you have high potential, you have a lot of potential, energy. You have a lot of potential to be able to fall down. When you have high electrical potential, charges have high potential to fall to lower potentials. So yeah, potential, electric potential, is pretty much the idea of kind of like electrical energy. And then the idea of voltage is that voltage is the difference between the high and low potential. So positive charges, right, they follow the rules. They go from high to low potential, just like a ball goes from high to low charge. But yeah, electrons that are bad, right? They're negative. They're mean, right? So yeah, they don't follow the rules. They're, like someone said in chat, they're bad. And protons are the good ones. They're positive. They're happy. Yeah. Mm-hmm. Yeah. But yeah, those are the ideas behind potential and potential difference. So the key idea is, if you want to make high potential, you can put a bunch of positive charges. And right, because what happens when you put positive next to positive? Do they attract or do they repel? Right, they repel, right? Since they repel, that's why positive charges go from high to low potential. They're repelled by the positive charges in high potential, and they move to lower potential where they're attracted by the electrons. And that's why electrons or negative charges in low potential go the other way. They want to be repelled by low potential and go to higher potential. Well, that's like kind of a simplified version, but works. And this is the idea of, and the idea of voltage is that we can have a difference of potential, right? If we have a high and a low one, right, we have a difference of potential, right? There's a difference between being high and, being low. So because there's that difference, it causes electrical charges to move. So it's like a locomotive is like a train that, moves along. The electromotive force moves electricity, moves along electricity. And the idea is voltage is the thing that moves it along. If there is a potential difference, then charges want to move, right? If we increase the potential difference, it's like we increase the height of a slide or something, right? Then the charges can move for longer, right? They want to move more. So that's the idea of potential difference or voltage or electromotive force. There's like so many names for the same exact thing, which is just basically the idea of kind of like increasing the amount of that charges want to move. All right, and then we have batteries. What do batteries do? Yeah, Richard, I did. Very good. Yeah. Right, so I see two different things. I see they store energy, they are a voltage source, and they charge the circuit. And yeah, and they store energy, then we use them. Yeah, so the idea of battery, right? is they store energy in chemical reactions, and then they're released to create an electric potential, right? This is something called a redox reaction. You don't have to know what that is, but it makes basically one side positively charged, one side negatively charged. So we have a potential difference. We have high potential on one side, low potential on the other. And that's why batteries can be used to power circuits, because they have potential differences. So that's why they can cause charges in a circuit to move, because they create a potential difference. And they store all the energy in chemicals, and they release it to create potential differences, which move charges along. Right. Right. So now here's the idea of current. Does anyone remember anything about current, or what current was? Ooh. Yeah. So I saw someone just type the letter I, and I actually agree. That one's a little interesting, why the letter I pertains to current. But I also see flow of electrons, right? We're not going to really see protons flow because protons are super heavy and they're inside the atom, so you can't really move them. That's why we see electrons move. Because they're tiny, they're outside the atom, they can move pretty easily. So current is going to be the flow of electrons, right? Protons are too big, they can't really move. So electrons are the ones that are going to be moving. And then current is basically how fast or how many electrons are moving in a certain amount of time, right? And then the letter we use to represent current is I. Oh, yeah, so someone said, what does move are electron holes. Yeah, so electron holes are, so electron holes are basically a lack of electrons. So there's some materials that have electron holes, or you can remove electrons from some materials, and those are holes. And then as electrons fill up those holes kind of move, right? Because like if you have a bunch of, let's say that we have a bunch of holes on the ground, right? Let's say we have a hole here, right? And then we have dirt here. What we're doing when we're moving electrons is we're kind of like digging up the dirt here, right? We're digging up the dirt here, and then we're moving it here. So it's kind of like the hole itself moved along. Yeah, so conventional flow, which is like the way Benjamin Franklin decided flow would be, current would be, the direction current is modeled in, goes from positive to negative. So it's the direction that electron holes kind of move in. But the things that are actually moving are the electrons, or negative charges, right? The flow of negative. Yeah. And then I saw some comment, I equals V over R. We'll talk about that really soon. Yeah, and then, yeah, that's the whole idea behind current. It's basically how many electrons move in a certain amount of time, or how many electron holes move in a certain amount of time. And then what they move through are these things called conductors, which are super good at letting electrons flow. I don't expect anyone to remember this, but the reason that metals are really good conductors is because they are basically this thing called a sea of electrons, which is basically like they have a bunch of electrons on the outside. So if you move one electron, they bump into a bunch of the other ones. So it causes a whole chain reaction of electrons to move. But something like rubber, they don't have that many free electrons. So then you bump one electron to the other, and it might not bump into another one. So it might stop, or it might not travel as fast, or not travel as well. Yeah, so electron holes flow in the opposite direction of electrons, right? If electrons go in one direction to fill up the hole, then you had to make a hole, right? It's kind of like, here's an electron hole, right? To move an electron here, we have to first dig one up. So if we dig one up, then we fill in this hole on the right side, right? It's kind of like the hole moved this way, but the electron moved here to fill in the hole. So electron holes kind of move in the other direction, opposite to the direction electrons move. Yeah. Okay. So that's the idea behind conductors. That's just the thing that electrons are actually moving through. And then we can get to the idea of basic circuits. So does anyone remember what the problem was with with just having a battery and a wire? Right. Mm-hmm. Yeah, exactly. It would burn out. The technical name would be a short circuit, or the way I like to think about it, it blows up and then you cry. Yeah, I like to think about it that way, right? Because, thank you. Basically, like, if you have only, yeah, it kills the battery, because basically let's say that we have no resistor, right? Then the electrons, right? There's nothing slowing down the electron. So all the electrons of the battery, they're going to flow all the way to the other side, and then we're not going to have any left, right? And because they flow so fast, that can cause things to heat up, right? If you rub your hands really fast, your hands heat up. So if you have electrons moving super fast, right, that could heat up, and it's potentially, you know, harmful. It's hazardous. You could, yeah, there could be bad things that happen. Hmm? You have a comment, David? Okay, then yeah. So that's why we need to add a thing called a resistor, which basically slows down the electrons. It basically makes sure that the electrons, right, they can they don't flow super fast, and they have ample time to actually, or like they don't flow so fast that they cause the circuit to like heat up and explode, right? So in order to prevent that from happening, we add resistance, which basically slows down the current. We can slow it to a manageable level. It's like having stop signs, right? Instead of having no stop signs at like an intersection, all the cars just crash into each other. We have stop signs, so they slow down. And objects that are really good at resisting current or slowing down current are things that are long, right? Because the longer it is, right, the more distance you have to travel, so the slower you move. Thin, because the thicker it is, the more, you know, the more electrons can flow at once. And then this thing called resistivity, which is basically like how good the material is at resisting current, right? High resistivity means it's super good at resisting current, right? Like maybe a puddle would slow everyone down compared to the normal road where everyone would not be slowed down. Yeah, thick with two C's. Those are bad resistors. You want thin ones, because then only like a few electrons can go through at a time. Right? And the objects that have high resistivity are called resistors, right? They are drawn like this, and they're basically just, you know, really long wire, really thin wire that have high resistivity. They can be made out of all sorts of materials, but usually you want ones that aren't very good at conducting, right? And you can think of resistance as basically the thing that's slowing down the electron, right? The electron wants to move as fast as it can, right? If you have no resistance, the electron's going to move so fast, it's gonna burn out the wire. But resistors make sure that they slow down, they take their time. All right, and now we get to the idea of Ohm's law. And this is the thing I saw in chat. So does anyone remember what Ohm's law is? Yeah, I see an equation in chat. A law, I agree, it is a law. I see multiple equations in chat, actually. I see two equations. One is V equals IR, and I equals V over R. Yeah, I also see someone saying that V is proportional to something. Yeah, so Ohm's law actually says that voltage is proportional to current. That's Ohm's law. But what most people think of, when most people think of Ohm's law, they think of this equation, which is V equals IR. Right? The idea that the more current you have, or the more resistance you have, you need more voltage. And the basic idea is, right, why do you have to increase voltage to increase current? Right, I see one answer in chat, right? You need, yeah, kind of. So the idea is, right, current is how many electrons are passing through at a time, right? How much charge is moving in a certain amount of time. Yeah, and then if you increase the voltage, you can get these electrons to move, you can get more electrons to move, or you can get them to, they want to move more, right? So more electrons are going to move, so we have more charge moving, and we have more current, right? It's kind of like if we, push, if we're in a pool or something, we can slowly push the water, the current would move, the wave would move really slowly, or we can push it really fast and we'd have a bunch of water going at a certain amount of time. Right? And then the reason you have to increase voltage for resistance is because, right, the more resistance you have, right, the more you have to push to get over that resistance. The more the more it resists, the more you have to push, right? The more voltage you need to get the charge moving, right? And then, so here's the equation V equals IR. You can rearrange it into these two forms, which some people do. But the idea of how you can memorize is this triangle here, where you're like V is equal to I times R, or V is over I, that gives R, right? V divided by I gives R, or V divided by R gives I. So that's the idea behind Ohm's law. I do Ohm's law in quotes because Ohm's actual law is technically just the idea that voltage is proportional to current, but it's more useful to know that V equals IR specifically. All right, and then there's another law, which is the power dissipation law, and this one's a bit harder. So why do resistors generate heat? Like they slow down charge. How does that generate heat? Yeah. Okay. Yeah, that's one of the key ideas, right? We can kind of think of resistors like basically adding kind of like friction to the system, right? Our hands, any surface has friction when you like when you rub them against each other, right? So when you think of charges moving across a resistor, right, they're being slowed by the resistor, right? So some of that energy of motion has to be changed into some other energy, and that energy is going to be heat, right? Another idea, right? If you like slap your hand, right, that hurts, it burns. Or if you like catch a baseball, or like I don't know what else, but like something suddenly stopping generates a lot of heat. That's why car crashes can cause explosions, because they generate a bunch of heat, right? And that heat that comes from the car slowing down suddenly. Resistors are going to suddenly slow down these electrons, and that generates heat. It turns their motion energy into like into heat energy. Yeah, like a soccer goalie, right? If they wear gloves, right, to kind of protect their hands, because it can burn if maybe like the ball rubs against them, right, scrapes against them, or like they catch it too hard, right, it hits them too hard. And yeah, the idea is heat is generated just because things are slowing down. And that heat is going to be generated in a certain amount of time. Oh, that's cool. My computer crashed. The screen just ended on me. There we go. Yeah, and the way that we can, like yeah, like in a lot of sports or like activities, there's a lot of examples of where friction can cause things to heat up. Yeah, exactly. Yes. Oh, okay, that's an interesting question. So the question is, will the resistor be hot if there are like 2 resistors by the battery and 5 others between them? So that'd kind of be like maybe like, say it's like this. So here's the battery, and then maybe we have like one resistor here, then we have like a bunch of other resistors here, right? So then how do we know which ones get hot? We know which ones get hot based on the power dissipation law. So we just need to know how much, we just need to know how much voltage, right, is dropping across each resistor and how much current is going across each one. So current in, as long as there's no junctions, right? Junctions are where there's more than one wire, right? So maybe one wire is coming in like this or something. That's a junction. As long as there's no junctions, current is going to stay the same. So current goes from positive to negative, right, like this way. So we have current flowing, right? So the current across each resistor is the same. So we just need to know how much voltage they have, right? And we know that V equals IR, right? So we know the voltage is proportional to the amount of resistance. So what that actually tells us is that it doesn't matter the position of the resistors. It doesn't matter which resistor is where. All that matters is the amount of resistance on the resistor. The more resistance you have on the resistor, the more power it dissipates. So the position doesn't matter in the circuit if it's just a series circuit, right? So like if we had 20 light bulbs lined up, all that matters is the resistance. We can switch around the order of the light bulbs. We can switch the order of the light bulbs around, and then we would have, but each light bulb would still have the same amount of power that it generates. The thing is, if we add more resistors, however, the voltage does decrease, because the voltage for each resistor decreases. Because if you remember Kirchhoff's second law, that tells us, right, each resistor, the sum of the voltages across each resistor can only be as much as the battery supplies, right? So the more resistors you have, the less voltage you have across each resistor, so the less power you have. But the position of the resistors doesn't matter. All that matters is the resistances on the resistors. So I had another question, which is why slowing down charge creates heat. Slowing down anything generates heat, because you have a bunch of energy when you're moving, right? You have kinetic energy when you're moving. So when you slow it down, that energy has to be stopped, right? When you stop moving or you slow down, you lose kinetic energy. So that energy has to be changed into some other energy. And then heat energy is one of the energies that's going to be created or generated when you slow down things, right? If you rub your hands together, right, one of your hands is slowing down the other hand at any time and it gets warm. When charges go against resistors, they're kind of like rubbing against the resistor. And when they slow down, that generates heat. Does that make sense why slowing down charge generates heat? Slowing down anything generates heat. Right. Right. And then here's like the triangle to remember P equals IV, because P over I is also equal to V and P over V is also equal to I. But the key idea is, right, the more voltage you have, the more current you have, the more power you can dissipate, right? The faster electrons were moving, the more energy you can get by slowing them down. The bigger the voltage across the resistor, that also means you can dissipate more power because you can have more electrons. You have more potential difference. So you want the electrons are going to dissipate more energy when they slow down. Okay. So here's like a sample calculation where we can actually work with the ideas of voltage, resistance, and current, right? So, right, let's say that we have a resistor with 2 ohms and an amp with 3, or we have a current of 3 amps, right? So we have this battery, it's providing this current across this resistor. And we want to figure out how much voltage is needed in order to get this 3 amps across the circuit. Right, so I saw someone give me the answer for voltage. Take a guess, or like tell me how you would calculate it if you don't want to calculate it. Yeah, so I see a few people giving me answers, and I see people giving me equations as well. Yeah, yeah. So the key idea is we can just use Ohm's law for the first one, right, to find the voltage, right? If we want to find the voltage, what's Ohm's law again? Or Ohm's law, the equation that we talked about? Yep. So that one is V equals IR. You can also write it as I equals V over R, as someone else wrote it. We're going to use V equals IR for this one because we want to find voltage, right? So we know V equals, our current is 3, our resistance is 2, so our voltage is 6, right? So that's how we know that this is 6 volts. And what about the power? Well, the power, P equals I times V, right? PIV. So we have 6 volts. So we know power is equal to 3 amps times 6 volts, which is equal to 18 watts. Right? So that was the answer to the second question, but a few people answered it already. So yeah, the power dissipated by the resistor would just be the volts times the amp, P equals IV. So we can just use these 2 simple equations to figure out a lot of information about circuits. And we actually only have to know information about this basic circuit because of Kirchhoffs Laws. So I spelled it wrong. That's cool. But Kirchhoffs Laws basically say 2 things. So the first one is the idea that current going into a junction is going to be the current leaving a junction, right? Just like traffic entering an intersection has to be the same as traffic exiting. What happens if more current enters than exits? What happens then? Why can't that happen? Why can't we have more current entering than exiting?
Law of conservation of energy.
Yeah, the law of conservation of energy. Yeah. You can't get energy from the ground or anywhere else, or you can't disappear current. Yeah, that's the idea, right? If you have more entering than exiting, where does the current go? Is it just gonna, right? Is it just gonna build up here, right? If we have a bunch of current entering, but only a bit exiting, are we just gonna have a bunch of current that's just stuck here, right? Where did the energy come from? Or like, where does the energy go? And if you have more energy exiting, right? That's impossible too, because where did the energy come from? You can't just get the energy from thin air, right? So that's why the amount of current going in has to be the same as the amount going out. And then the second law is Kirchhoff's loop rule, which basically says the voltage across a loop is 0. It also says that the voltage supplied by a battery is going to be the same as the voltage drops across each resistor. Yeah. Exactly, right? The conservation of energy says energy, it can't be created, it can't be destroyed, right? It can only be converted. We can convert it from kinetic to heat energy like we did with power, but we can't just suddenly make it disappear, right? So that's why the amount of energy coming in has to be the same as the amount coming out, right? Energy can't suddenly be created out of thin air. So that's the idea of the junction rule. And the loop rule, right? If we have more voltage each time we go across the loop, we're going to get more and more and more voltage every time we go across the loop, which means that we suddenly get infinite voltage after we go across the loop enough times. That doesn't make sense. And if we lose voltage, then we get negative infinite voltage. That also doesn't make sense. So that's why across a loop, we have to maintain 0 voltage every time we go across the loop. We have to have a net of 0 volts. Otherwise, we would increase voltage or decrease voltage, and that'd be bad, right? And then the reason that Kirchhoffs laws are so important is because along with Thevenin's and along with Norton's theorem, we can combine pretty much all the different circuit parts into a single circuit. Right? Thevenin's tells us it has a V in it, so it tells us we can combine voltages. And then the Norton's tells us current, how current can be combined, current sources. And then Kirchhoffs laws, if you rearrange them, they can actually tell you how resistors can be combined. What's a junction again? So junctions are basically just any time. So here is like one wire, right? We can bend that wire. So we can bend that wire like this. It's still not a junction. But if we have two wires intersecting, so let's say we have one wire here and another wire here, right? If we have two wires intersecting, the junction would be right here, right? Junction is right here in the middle, where two wires intersect, right? This might be one wire intersecting another one. So junctions are where maybe two wires intersect. If it's just one, it's not really a junction. Yeah. So the idea is like, if two wires both bring in current and they both give out current, right? We would have the same amount of current coming in as the same amount that's exiting. So that's another question, can't the missing current stay in the resistor? Junctions are loops. Junctions are where wires meet. You wouldn't see junctions with like two resistors meeting. So you wouldn't really see like this, two resistors touching in a junction. You'll see two wires. Wires can't really store electrons, right? Because the point of a wire is that it's a good conductor, so electrons move super easily across them. So they can't really store. Current or like charge. So that's why. So that's why it's not just like. So that's why it can't just be like stored inside here. You can't just have more that's stored inside here, because then it's kind of like the idea with the metal and like with all the electrons here, right? You move one electron, all the other electrons are going to move too. Right? You can't really store them or squish them together because they're already like, there's already so many electrons that moving one is going to move all the other ones. Does that make sense? Why it doesn't just, okay, cool. Yeah. The main idea is like, it's not, it's where wires intersect, not where resistors intersect. Yep. Right. Okay. So now let's introduce the idea of a capacitor in our circuit, right? So capacitors, right? They store electrical potential energy, and they look kind of like this. They look like two plates, right? One side's charged positive, one side's charged negative. Right? It's kind of like a battery. And then there's going to be a voltage across them, potential difference, because we have positive and negative, right? And then things that make good capacitors have big plates and small distances between the plates, right? But the idea with capacitors is that they have this thing called capacitance, which is basically how good they are at storing charge, right? So if we have a certain amount of voltage, right, the bigger the capacitance, the more charge you can store on your capacitor, right? So what kind of energy do capacitors store again? They do store energy, but what kind of energy? There's a bunch of different words that could describe the kind of energy. Right. I like the idea. Yeah. Potential and electrical. Yeah. Yeah. They store charge on them, and as such, they store electrical energy. And that energy, that type of electrical energy is potential energy because it's stored inside of the capacitor, right? It has the potential to move, right? It's not moving right now. The current is stored inside the capacitor. It's not moving, so it has the potential to move. right? So it's potential energy, and it's electrical, because capacitors store charge, right? You might have a bunch of electrons on one side, and you might have a bunch of electron holes on the other. Then we have electrical energy that's stored. Yeah. So potential and electrical are the two ideas, right? And here's how we can charge a capacitor, right? So we might have a circuit like this. This would be an RC circuit because it has a, or why do you think it's called an RC circuit? Where does the R come from? Where does the C come from for RC? Yeah, right. R comes from resistor and C comes from capacitor. Yeah, someone said the resistor and capacitor. Yep, and it has both a capacitor and resistor. Yeah, exactly. Right, it has both a capacitor and a resistor. Okay. Capacitors, right, they have the capacity to store electrical charge. Resistors, they resist motion, right? So that's where the idea of RC comes from. What's the reason we need a resistor again? Why can't we just why do we need a resistor in a circuit again? Exactly. Yeah. The idea that, right, since capacitors don't have resistances, without a resistor, it's gonna short circuit, and the whole circuit might explode, right? Like if you short circuit a light bulb, that could cause it to spark and explode, or at least like old light bulbs, they used to have like oxygen in them, so they would blow up if you had a bit of heat. Yeah. So here's the idea of charging a capacitor, right? Slowly, the voltage across the capacitor is going to increase, right? And then why does the voltage across the resistor decrease? When the voltage across the capacitor increases, why does the voltage across the resistor have to decrease? Right, it's kind of like the idea of the capacitor taking it all, right? Because Kirchhoff's loop rule says across the loop, the voltages have to be the same, right? So if the battery is providing a certain amount of voltage, right, the resistor has to lose, the resistor can lose some of the voltage, the capacitor can take some of that voltage, right? So if the capacitor is charging up, it's taking more and more voltage, so the resistor is getting less and less, right? So when the capacitor is charging, the resistor loses voltage. When the capacitor is discharging, the resistor would gain voltage, right? If the voltage across the capacitor is decreasing, the resistor would gain voltage. And then why does current fall if the voltage across the resistor fall? Why does like voltage falling cause current to fall? Anyone remember like a law? Or just like a general idea of why that might happen? Voltage. Yeah, so it has, oh, yes. Yeah, right. So someone said voltage proportional to current. That's fine. I can't spell either. Voltage is proportional to current, and low volts means low current. Yeah, so voltage is proportional to current. That's Ohm's law. Yeah, so that one's Ohm's law. Kirchhoffs laws have to do with conservation of energy and stuff, but Ohm's law has to do with voltage and current, right? Ohm's law itself says voltage is proportional to current, right? That means if voltage decreases, current also decreases. So that's why when the voltage decreases across the resistor, the current decreases, right? It's kind of like when you're charging a battery. You can think of capacitors as batteries, right? When you're charging a battery, you don't want the current to be the same. You don't want it to keep charging even though the battery's full. You want it to stop charging. You want current to stop flowing through your capacitor once it's fully charged, right? So that's why that's why it's good that current decreases, and it makes sense that current decreases. As you're charging it up, right, the current's going to decrease, right, because you don't want to charge it anymore once it's like pretty much full. Okay? And now we can get to the second weird component. So first we had the inductor that stored electrical potential. What does the inductor store? Anyone remember? Actually, we can get to that question later. Let's first talk about the idea of magnetic flux, right? Does anyone remember what flux is? It's a really weird word. What does it stand for? Yeah, right. I like the idea where people are mentioning fields. Right? It's basically like how much electric field we can catch in a or magnetic because it's magnetic flux. It's basically how much magnetic field we can catch in a certain amount of area, right? The bigger our basket, right, the more magnetic flux we can catch, right? And that actually comes to the second idea of, maybe the idea is a bit later, but yeah, basically magnetic flux is how much of the magnetic field you're catching, right? If you're not catching any, you don't have any flux. If you catch more and more, you have more flux. And the key idea with magnetic flux is that there's this thing called induction, which says that current can create magnetic fields, which creates magnetic flux. Right? So if we have current across a wire, we can induce magnetic fields. We can cause magnetic fields just appear. And then these can be caught by the wire, and then we get flux on that wire. And that's exactly what inductors do. They're loops of wire, right? They look like this. They're just loops of wire around some, usually you have them around some metal, like iron is a really good one. Another one is ferrite, which is like an iron derivative. And basically the idea is, right, when current passes through them, they induce magnetic fields, right? So we have magnetic fields induced. And the reason that we have a bunch of loops is because the more loops that we have, the more magnetic flux we can catch, right? So the kind of like more magnetic, kind of like magnetic energy we have. Right? We basically have stuff stored as in the form of magnetism. Yeah, so the wire itself would be made out of copper, yes, right? That's usually what inductors are made out of. They have copper wires wrapped around iron. The reason it's wrapped around iron is because the magnetic field can pass through iron really easily. So then you have like, what you would have is you would have like a copper wire like this. And then you have a iron thing inside there. So what's happening is you make a magnetic field, and basically the magnetic field passes through the iron, while the current is going to travel through the wire this way. Yeah. Oops. Let's clear that. Okay. Right, so that's the idea of an inductor. They basically take electrical stuff, right? You have current passing through them, and they convert it into magnetic stuff. They generate magnetic flux from them. And inductance just basically tells you how well it can charge. This is a weird formula. I don't really care about the formula, but if you want to know what inductance is, this is the formal definition of inductance, which is like how much or how well changing current can generate an EMF. It's basically like how well an inductor can charge. And then we have this little thing here, XL. This thing is called reactance. That's one of the much harder concepts. And that's basically the idea that inductors, as they generate these magnetic fields, they have less and less resistance to them. So that means current, right? While they're generating magnetic fields, current flows more easily through them. It's kind of like the magnetic fields are kind of like sucking up the current. They're causing more current to flow and letting more current flow through. So it gets easier and easier, right? So it's kind of like we had a bunch of resistance and it slowly disappeared. And that resistance that disappears is called reactance. Right? It's basically like the amount, it's like the thing that opposes current from going through inductors. But as inductors generate magnetic fields and get magnetic flux, they let current pass easily and easily. So the reactance is going to decrease. But reactance opposes current, right? So I saw someone ask what all of these things are. So V is voltage. Oh, you didn't ask about that. L is inductance. Inductors start with L for some reason. I don't know why. Probably because I was taken by current. So then they were like, oh, we got to find some other letter. X is reactance. And then omega is this thing called like basically the angular velocity. These things are really weird. But the key idea is basically like here, this thing just represents that we're changing current over an amount of time. This is an omega, it looks like a little W. The idea is like if we change current, right, that causes a voltage. That causes a change in voltage across the inductor. And the idea is when voltage is small, right, as voltage decreases across the inductor, the change in current is also going to be small. But I don't think this equation is necessary. I don't think you need to know this. I don't think the idea of inductance is really that important either. I think the key idea that like this is more like this is like a really hard concept because it has to do with the idea of like alternating currents and like the period of which like how long it takes from current to oscillate from an inductor to a capacitor back to inductor and capacitor. But like, yeah, I think the key idea is just like the idea that inductors generate magnetic fields because you change the current, and that in turn lets you be able, and then you can convert that magnetic field back into voltage because of inductance. XL is like the reactance of an inductor. Reactance is basically the thing that like opposes your current, right? So inductors at first, they're really hard. It's really hard for current to pass through inductors. So if you have an inductor and then you have a resistor, the current is going to want to go through the resistor. Right? If you have right? Electrons might be able to go through like both of them, right? If they had to choose, they would want to go through the resistor because it's so hard to go through the inductor. But as inductors start generating magnetic fields, as they generate magnetic fields, then they, instead of going through the resistor, they're like, oh, it's easier to go through the inductor now. It's easier and easier. So it's kind of like the resistance of the inductor is decreasing. And that resistance that kind of like decreases is called reactance. It reacts against the current, and it's proportional to, or it's like inversely proportional to how much current is passing through, right? So as more current passes through, right, the easier it is to move. It's kind of like one way I like to see. One way I like to think of it is like, let's say that we have a water wheel, right? Or just like maybe like I don't know, maybe we have like a spinner, like a fidget spinner or something like that, right? The first time you spin it, or it's like really hard to get it moving, right? As the first time you hit it might be harder, but as it's moving, it's easier and easier to keep it moving, right? Just like maybe a carousel. If you've ridden a carousel with your friends, it's really hard to get it moving, but once it's moving, it's really easy to keep it moving. So reactance, right? As current goes, our motion's kind of like the current. As we increase the amount of spinning that this carousel is doing, that's kind of like we're increasing the amount of current in our circuit. So that's why it's easier and easier. So there's less and less reactance. And that's the idea of reactance. It's like basically the thing that opposes you from keeping the current going through that thing. But as more and more current goes through, you have less and less reactance. It's easier to maintain current going through it. Does that make sense what reactance is? XL is the reactance on the inductor, and it's basically a measure of that resistance that comes from current not going through it in the first place. Okay. Yes, that's one of the hard concepts. I would ignore omega, I would ignore T. I really didn't cover that stuff, but understanding reactances, pretty much like understanding why why inductors like act the way they do. Yeah, right. So if we're charging inductors, here are the charts. Basically, the idea is, right, current is going to increase across the inductor, right? It's going to be easier and easier to get current to go through the inductor. But as such, we have less and less voltage across the inductors, actually, because it's storing more of it in magnetic fields and magnetic flux, right? So it's going to be able to store it in magnetic flux, so it doesn't need them as voltage, right? EMF, voltage is EMF. That's electromagnetic. We don't need electromagnetic. Electromotive. We don't need electromotive. We want magnetic in inductors. So that's why the voltage is going to decrease. So then we can think about putting inductors and capacitors together, right? And that's the idea of this thing called an LC circuit, right? And basically an LC circuit, you have an inductor. What kind of energy does it store? Yep, potential. And what kind of potential? So we said that capacitors stored electric potential. What do inductors store? Yeah, potential energy. a specific kind of potential energy, and that would be what kind of fields do they make as current passes through them? Yeah, they make magnetic fields, yeah. So they store magnetic potential energy, yeah, right. So idea is inductors, they store magnetic potential, capacitors, they store electric potential, and then basically energy is going to oscillate from being stored in magnetic to electric, to magnetic to electric, right? We can think of that as that little bowl, right? That bowl where we have magnetic here, electric here, and it's going to bounce, like the energy is going to oscillate between here and here. Like kind of like a skateboarder goes from here to here to here to here, or like a ball rolls down a hill and will back up the other way and back up and back up and back up. It's going to oscillate between magnetic, electric, right? And then where that omega thing comes in is basically like how fast it's oscillating. Omega kind of tells you like how fast it's oscillating between magnetic and electric. That's why it's one of those harder concepts, because it only comes up in LC circuits where we have this field, or we have this energy oscillating between magnetic, electric, magnetic, and electric, right? Yeah, so that's the idea behind LC circuits, right? So why is this type of current called AC current? Why is it called AC? Like, what's happening to the current? The direction of the current? Yeah, I like that answer. So someone said it's alternating. Yeah, it's alternating direction. That's why it's called alternating current. Yeah, alternating current stands for, the abbreviation is just A for alternating, C for current. AC put together. Yeah, that's the idea. Yeah, so we have alternating current. Right before, we only had current going in one direction. The battery told us the way the current went. But now, if we have these two different types of energy storage devices, we can create alternating currents. We can have the current alternate between them and change direction back and forth. Right? And that's, yeah, that's one of the key uses of inductors and capacitors, right? Create alternating currents. Right? And the fact that like our power outlets, those use alternating current, right? So our computers, our devices, they all charge with alternating current. So that's also why they tell you not to put magnets near your devices, because they use alternating currents, right? They probably have inductors in there. And if you put in a magnetic field, you're going to mess up the inductors. That's going to mess up your device. And you can also move all the electrical charges while using magnets. Because right, magnetic field, if you change the magnetic field, you induce a current that causes your charge to move. Right. So now we get to the final section, which is the few other devices, the other miscellaneous devices, right? We have an alternator. What did an alternator do? Does anyone remember? Alternator. Sounds like a concept that we just talked about. I'm not sure about the spelling, but yeah. Oh, yeah. Yep, it alternates current. Oh, yeah, because the N is next to the spacebar. I see. Yeah. It basically alternates current. It's another way we can make alternating current, or AC. Right. Yeah. And basically, it converts a DC current into AC. So this is the setup. It's really complicated. We talked about it a little bit. If you want to review how it works, I have that thing in Google Classroom, which is really nice, which in explaining how it works, a little video. But also you can review the slides from last week where we talked about it. But the idea is we use DC, right, to spin this, or we spin this hoop, right? We can use DC to spin this hoop using a motor, which we're about to talk about. And basically, right, as this hoop changes the direction here, right, as the hoop becomes vertical, what happens to the flux it captures? I can go back to this picture over here, right? As the hoop becomes vertical, what happens to the amount of flux it's capturing? Yeah, right, more flux, yeah. Right, yeah, I saw multiple people say that. That's great, yeah, it gets more flux, right? So the flux is increasing, but then as the loop goes like this, what happens to the flux? If it gained it going this way, what happens as it goes the other way? Yeah, exactly, it decreases. So you start by increasing flux, then you decrease. When you increase flux, you generate current in one direction. When you decrease flux, the current's going to go in the other direction. And that's the whole idea. The current is going to go in different directions across the hoop. And the way we could use DC to spin this hoop is using something called a motor, where Right? Basically, the key idea of a motor is we use charge, we use current to create a magnetic field, right? We induce a magnetic field, current, magnetic field, and then what happens is this magnet wants to spin around, right? North wants to attract south, south wants to attract north, so it spins around, but as it spins around, suddenly these nodes on the hoop are going to hit other sides. This pink one is going to suddenly become negative, and this blue one is going to suddenly become positive, which flips it around. So now the north, right? The north originally wanted to spin, so it's facing this direction, right? It's facing the south, right? And the south wants to be here. But then, because we switched the current, right? We flopped the current. We also flopped the direction of the magnetic field. So now it flops back to here. So it resets itself, and it spins again, resets, spins again, resets. That's how a motor works. And then we have two really quick things. The first is a diode. Right? Diodes basically let current only in one direction. So current's only going to flow in one direction in the diode. And diodes are helpful because you can tell what direction they flow in if they're made out of a forward bias PN junction, because they point in the direction they flow in. Current just can't flow in the opposite direction. Right? So if you attach it to AC current, right? Let's say that we had an AC current. Right, here's maybe some AC current source, right? And then we had a nice diode here, a little diode, right? Right. What happens is, right, when current flows in this direction, can it pass through the diode? Yeah, yes, it can, right? See that? And then if we go this way, can it pass through the diode? No, right? Because it's going opposite the direction the diode's pointing. So the idea is, right, alternating current, it only passes through the diode 50% of the time. But the way that it passes through is always in one direction, so it's direct, right? It's in one direction, so it's direct. But let's say we wanted to capture all this alternating current and turn it to direct current. Then we would use something called a rectifier, which looks just like this. It's just a way you can arrange these diodes so that you can catch on both sides, right? If you go this way, you catch it on this side. Right? So if it goes this way, you catch it on this side. If it goes this way, you catch it on this side. Right? So that's the idea of a rectifier. It's basically a way you can arrange diodes in order to catch this AC and turn it all into DC. Right? One diode, we said, only catches 50%. Right? We showed why. It doesn't catch it going the other direction, but it catches it going one direction, but not the other. But this rectifier can catch it in both directions and turn it into a single direction. All right, so that's the idea of a rectifier. And then that's the last device we'll talk about. So yeah, that's pretty much it. Does anyone have any questions or want me to go over some of the other concepts? Because I kind of sped past inductors. If you have any more questions about inductors, feel free to ask, because those are really hard. Anything to do with magnetic fields are really hard. If anyone has any questions about any of these devices, you can also ask, because these are like, the way they work is kind of weird. Yeah. Oh yeah, so here with a motor, basically like we said last week, this thing, the bottom part is always going to provide one charge, and the top part is always going to provide another. So basically when so basically they reset because kind of like the magnet kind of resets, because let's imagine this hoop is spinning, right? So once this hoop spins so that north points up and south points down, right? That means that it's spun like about 90 degrees. So this blue part would spin to, the pink part would spin to here, and the blue part would spin to here, right? Right. So then, because of that, right, if we go any further, then the blue part is going to touch this positive charge, right? And this pink part is going to touch this negative charge. So then suddenly, the direction of current, instead of flowing from, it used to flow from pink to blue, now it flows from blue to pink. So then our magnet is going to suddenly switch directions. It's going to suddenly flop. Instead of being like that, upright, it's going to flop upside down, because we switched where the blue was, where the pink was. So now our magnetic field looks like that. And then if we keep spinning, then it'll reset, right? It'll go back to here, and then it'll move up, and it'll flop back down. So it's kind of like it goes this way, then this way, then this way. And suddenly, when this blue charge touches, when this blue part of the hoop touches this positive potential, suddenly the north flips around, and then it goes back. So it never points in this direction. It's kind of like it never points in the correct direction it should be. So it's always resetting and resetting and resetting, so it can keep on spinning and keep on spinning. Does that make sense? Okay, yeah. Right. As soon as that blue touches the positive potential, flips around. The magnet flips direction, right? And that's how we keep getting it to reset and reset and reset. Good motors will actually have a bunch of hoops, right? We'll have a bunch of hoops perpendicular to each other. So it doesn't have to suddenly jerk and reset like that, because each one can be kind of like continuous. It's like it's kind of like if you have one hoop, right? If you're spinning like one hoop around, right? You have to spin it every time this hoop comes around. So you can do it once, and then it spins around once, and then you hit it again, and hit again, and hit again. But if you have a bunch of them, right? That's kind of like if you have a bunch of stars on, or like a bunch of points on a spinner, you can hit this one, and you can hit this one, this one, this one. So you can hit it more continuously. You can get it to spin more smoothly. So good motors will have a lot of hoops, so they can spin kind of more smoothly. Yeah. All right. That's a good question. How does the magnet go to the north side? Why doesn't it go to the south side? To the north side of the magnet. I just didn't draw the south side, but the south side is always opposite to where the north side is. What I drew is this thing called a magnetic dipole, which is like the direction. It's kind of. So the north side's here, the south side's here. As it's spinning, what the actual magnet will look like. So here's the north side. North side might be spinning up and then suddenly flops around like this. And what the south side will be doing, here's the south side. It's connected to the north side. It's opposite to the north side. So the south side is going like this and then like this. So the south side is also flip-flopping. So it's kind of like you have a magnet, right, and you're spinning it, and suddenly you flop its direction, and then you keep spinning it. Yeah, like that. That makes sense. That south side still exists. It's just that it's easier just to draw one side. That's why. Yeah. Why doesn't the north side of the center magnet go to the south side of the other magnet? Oh, yeah. So it wants to go to the south side, right? The north side really wants to go to the south side, right? This north side, it really wants to turn and move to the south side. That's why the hoop is going to spin. But the thing is, before it can reach the south side, right, the hoop is spinning in this direction, right? So before it can move to the south side, it suddenly flops because the charges, right, the charges here are flopping. Right? Suddenly blue is positive and pink is negative. So suddenly it's flopping. So the magnet is going to flip to the other side, but it's still going to spin in this direction. So it's going to keep spinning and spinning. And then it's going to flop again because now the blue, right, is going to go back to the blue. So it's going to be back to negative and back to. So it wants to go to the south side. It's going to keep trying to spin to get to the south side. But because we flop the charges, we never let it touch. We kind of like skip over it. That's what like this thing does. It kind of like skips over it touching the south side. It jumps over. It's like if you've ever played that like game where you have like that ball and then you attach it to your ankle and then you're like jumping over it. You can think of this as the south side, right? We're kind of like jumping over it each time, so we're never letting it touch. By flipping the current, we're kind of like jumping over the south side. We're never letting it touch the south side. We're always getting it back to the north side, getting it back to the north side, getting it back to the north side. Yeah. So it wants to go to the south side. It just can't because we don't let it. We don't let it because of this thing. Because we flip the charges to say, no, don't go to the south side. Go back to the north side. Go back to the north side. Go back to the north side. That's what flipping the charges is doing. Right. Does that explain why it never touches it? It wants to. It really wants to. But by flipping the charges, we're saying, no, you're not allowed to. Go back to north side. All right. Okay, that's good. All right. Then that's it. If you want another explanation, remember on the Google Classroom, I put that animation. It's really helpful in showing why the magnetic field is going to flop, and like it actually shows 3D stuff, which I can't really do. What happens? Oh, I missed that question. Yeah, what happens when you blow a fuse? So fuses are really good devices because what fuses do actually, fuses, I think in your house it's a circuit breaker, but a fuse is basically this wire, right? Basically, the idea is, right, wires, resistors, resistors heat up, right, if you pass too much current through them. So if you plug in too much devices, right, it's too demanding. It's pulling in too much current, so that causes the fuse to heat up and it burns. So that's why the fuse suddenly, it burns, so it breaks the circuit. If it burns, right, this thing is gone. So the circuit's broken. So that's why the circuit might stop working and you might not be able to charge. On the other hand, what your house probably has is a circuit breaker because you can flip a switch. And basically what it does is once enough current passes through it, it flips a switch and it stops the current from passing through it, flips it. So it's saying, no, current, you're not allowed to pass through. There's too much. That's going to harm the other wires. If more current passes through, it might burn these wires. So you have to unplug some stuff and then flip the switch back. Yeah. Yeah, exactly. Right. You'll need, the problem with fuses is they burn out, so you need to replace them. But with circuit breakers is they're kind of like a switch. So you can easily just switch them back. You know, flip them back and they're all good. And it resets. Yeah. Yep. Yeah, that's a good question. That's a device I didn't talk about. One of those devices I didn't talk about, but they're still super useful. Yeah. And they just go with the idea of like, you know, resistors dissipating power. What they mean. All that means is like if you have a fuse, right? If you have too much current passing through it, right? P equals IV. The more current we have, the more power we make. So the more heat we have. So if we have too much current, we have too much heat, and that burns up the fuse. So it stops the circuit. It breaks the circuit by breaking the wire. The fuse is like a little wire, and once it gets hot enough, it breaks it. And then, yeah, a circuit breaker is going to like be a switch that flips. On the other hand. All right. Yeah, so thank you for coming. If you have any questions, you can feel free to stay back, or you can